Every year, about 11 billion tons of goods move across the world's oceans. Your phone, your clothes, the grain in your bread. And almost all of it arrives on a ship. And almost all of those ships run on the same thing they have for over a century. A thick, viscous residual fuel called bunker fuel. The kind of stuff that's left over after refineries have extracted everything more valuable. There are roughly 105,000 merchant vessels operating today. Together, they produce around 1 billion tons of carbon dioxide every year. That is about 3% of global greenhouse gas emissions. If international shipping were a country, it would rank as the 6th largest emitter in the world, sitting between Japan and Germany. Nobody really talks about this. Shipping is invisible infrastructure. It works so well, so quietly that most people have no idea it exists, let alone that it has a serious emissions problem. And it is a genuinely hard problem. Unlike cars, you cannot just bolt a battery onto a container ship. The energy density requirement for a vessel crossing the Pacific are enormous. You need fuel that packs a serious amount of energy into a manageable volume and weight. Bunker fuel does that well, and most alternatives do not, at least not yet. So the industry has been stuck and the regulators have been pushing. In 2023, the International Maritime Organization set a binding target for net zero emissions from shipping by around 2050, with interim checkpoints of 20 to 30% reductions by 2030. These are now mandatory for large ocean-going vessels. And now the pressure is real. The question is what you actually burn instead. Hydrogen sounds clean, but storing it on a ship is a nightmare. It has to be kept at negative 253 degrees Celsius, just above absolute zero, or compressed to extreme pressures. The infrastructure barely exists. Liquefied natural gas, or LNG, is cleaner than bunker fuel, but it is still a fossil fuel, and ships built for it today risk becoming stranded assets before they are retired. Ammonia is the one that keeps coming up. And in November 2025, a company called Everllence held a 2-day conference in Copenhagen for over 300 people from across the maritime industry. They had something to show. This is the story of why ammonia, why now, and whether it is actually going anywhere. Ammonia is not a new idea. We have been making it since 1913. It is the backbone of the global fertilizer industry. About 80% of everything produced goes straight into agriculture. The infrastructure, pipelines, terminals, tankers already exist across every major port in the world. That matters more than people realize. You do not need to build a fuel supply chain from scratch. It also has no carbon in it. The molecule is just nitrogen and hydrogen. Burn it and in theory you get nitrogen and water. Nothing else and no carbon dioxide. Compare that to hydrogen, the other zero carbon candidate everyone talks about. Hydrogen has to be stored at negative 253 degrees Celsius, just 2 degrees above absolute zero, or compressed to extreme pressures. On board a ship crossing the Pacific, neither is practical. Ammonia liquefies at a far more manageable negative 33 degrees. It's cold but not cryogenic. And the shipping industry already handles it as cargo. So on paper, ammonia looks like the answer. It's got its existing infrastructure, there is no carbon, and also it can be stored manageably. The industry has been circling it for years. Here is the problem. Ammonia burns badly. Its auto-ignition temperature is around 630 degrees Celsius. Diesel, on the other hand, is 210. It has a slow flame and also a really poor combustion stability. And when it does not burn completely, which happens a lot, it slips out of the engine as unburnt ammonia. And that is really toxic. It also produces nitrous oxide, a greenhouse gas roughly 270 times more potent than carbon dioxide. An MIT study published in 2024 warned that switching the global fleet to ammonia under current regulations could cause up to 600,000 additional premature deaths per year from air quality impacts alone. That number assumes the worst case, but it is not a number you can ignore. So the question was never whether ammonia could work in theory. It was whether you could build an engine that handles it well enough in practice. Formerly, MAN Energy Solutions, one of the largest marine engine makers in the world, has been working on this since at least 2021. Their approach is the dual fuel concept. The engine runs primarily on ammonia but uses a small amount of diesel as a pilot fuel to ignite it, around 5% diesel and 95% ammonia. It's enough to solve the ignition problem without abandoning the zero carbon goal entirely. They call it the MELGIA, liquid gas injection ammonia. It is a 2-stroke engine, which is standard for large ocean-going vessels. It's slow, powerful, and also built for the long haul. Testing began on a single cylinder at the research center in Copenhagen. More than 12 months of that before they stepped up to a full-scale engine in November 2024. Then in January 2025, they ran it at 100% load for the first time. The fuel injection system validated across the entire load curve. In November 2025, they unveiled it formally at a maritime conference. The first engine deliveries are scheduled for 2026, a 200,000 deadweight ton bulk carrier in Japan. A joint venture between 3 Japanese companies is said to be the first commercial vessel fitted with the one. But here is the uncomfortable question nobody wants to sit with too long. Does burning ammonia actually solve the emissions problem, or does it just swap one for another? The concern is actually real. Ammonia combustion produces 2 things you do not want. The first is nitrogen oxide, the same stuff that causes smog and acid rain. It has been regulated in shipping since 1997. The second is ammonia slip, unburnt ammonia escaping through the exhaust. At 25 parts per million, it becomes dangerous in enclosed spaces. At higher concentrations, it is acutely toxic. And then there is N2O, nitrous oxide, a greenhouse gas with a global warming potential roughly 270 times that of carbon dioxide. If ammonia engines routinely emit even small amounts of it, the math on decarbonization gets complicated fast. These were the numbers that made the MIT study alarming. Worst case assumptions, but not invented ones. Here is what the testing actually showed. On the MELGIA, ammonia slip came in below 10 parts per million during full-scale operation. NOx emissions tested lower than equivalent diesel operation, not higher. N2O came in below 3 parts per million, and critically, these results were achieved without exhaust after treatment. No additional catalyst system required. That last part matters a lot. Every system you bolt onto an engine adds cost, complexity, and maintenance. An engine that hits acceptable emissions number without after treatment is a fundamentally simpler product. It's more reliable and also easier to crew. WinGD, Everlence's main competitor in the 2-stroke ammonia engine space, reported similar results from their own testing. Ammonia slipped below 10 parts per million. NOx meeting IMO Tier 2 standards without the DNOx system. Tier 3 compliance, the stricter standard applied in designated emissions control areas. It's achievable with a selective catalytic reduction system added downstream. The irony is that ammonia itself becomes part of the solution here. In an SRC system, ammonia acts as a reductant that converts NOx back into atmospheric nitrogen and water. The fuel and the cleanup agent are the same molecule. This is not fully solved. Regulatory frameworks for ammonia emissions at sea are still being written. The IMO interim guidelines are exactly that, interim. What counts as acceptable ammonia slip from a vessel operating near a port, near people, is still being negotiated. And the worst case scenario, a large ammonia leak not from the exhaust but from the fuel system itself, requires entirely new onboard safety infrastructure. Detection systems, ventilation, emergency protocols, training, all that. 150,000 hours of engineering and 800 tests got Everllence to an engine that works. The safety envelope around that engine is still being drawn. A Japanese bulk carrier is going to run on it. That's really great. But where does it actually bunker? Right now, almost nowhere. There are roughly 140 port areas around the world that handle ammonia in some capacity. Pipelines, terminals, storage tanks. But that infrastructure exists to move fertilizers, not to fuel ships. The distinction matters. Bunkering a vessel is a completely different operation to offloading cargo. You need dedicated berths, safety framework, trained crew, emergency response plans, regulatory approval. None of that exists at scale yet. Rotterdam is the furthest along. In April 2025, a consortium of companies transferred 800 cubic meters of liquid ammonia between 2 vessels at the Maasvlakte terminal. It took about 2.5 hours, and luckily nobody was injured. No ammonia was released into the port. That sounds like a low bar, but in the world of new maritime fuels, a successful pilot without incident is genuinely significant. It moved Rotterdam's port readiness level to 7, meaning project by project bunkering is expected to be approved in 2026. Singapore conducted the world's first live ammonia bunkering trial in March 2024. Japan has ordered its first dedicated ammonia bunkering vessel expected in 2027. Norway has permission to build a terminal. That is more or less the list. Compare that to LNG. Roughly 7% of the global fleet can already run on it. The bunkering network spans dozens of major ports across every ocean basin. It took decades and enormous capital investment to build. Ammonia is starting that process now. There is also a volume problem that does not get discussed enough. Ammonia holds less energy per liter than bunker fuel, about 1/3 less. So a ship that currently bunkered once on a given route would need to bunker more frequently or carry larger tanks, or sacrifice cargo space. Naval architects are redesigning vessels around this. It is manageable, but it is not free. And then there is the supply question. The ammonia that exists today, the stuff in those 140 port terminals, is made from natural gas, grey ammonia. It produces carbon dioxide in its production even if it does not produce CO2 when burned. Green ammonia, made using renewable electricity to split water into hydrogen and then combining that hydrogen with nitrogen, is where the zero emission story actually holds. But green ammonia production is still tiny. DNV estimates confirm plans to bring it to about 14 million tons per year by 2030. The shipping industry alone would need several times that to make a meaningful dent. So the honest picture here is this. The engine exists, a handful of ports are preparing, 39 vessels are on order as of late 2025. The regulatory pressure is real and tightening, but the infrastructure is years behind the technology. And the fuel that the technology actually needs, green ammonia at scale, is years behind the infrastructure. That gap is the whole story. Here is where ammonia actually stands. As of late 2025, the total alternative fuel order book across the entire global fleet is 1,942 ships. Of those, 1,259 are LNG, 385 are methanol, and 45 are ammonia. 45. Methanol is not waiting around. Maersk, CMA, CGM, COSCO, the biggest names in container shipping, have all committed. More than 60 methanol-capable vessels are already on the water. Around 300 more are on order. 20 ports can bunker it today, and Maersk alone plans to operate nearly 20 methanol dual-fuel vessels by the end of 2025. Ammonia is still approaching proof of concept. Methanol is already at early scale. They are not in the same race right now. Part of this is chemistry. Methanol is liquid at room temperature. It handles like diesel. You can store it in modified existing tanks. Training crews on it is difficult but manageable. Ammonia requires entirely new safety protocols, new storage systems, new everything. The learning curve is steeper and the consequences of getting it wrong are more severe. A methanol spill is bad. An ammonia leak in a port is a different category of problem. Part of it is also timing. Methanol got a head start. The industry committed capital to it first. Capital begets infrastructure. Infrastructure begets more orders. Ammonia is now trying to build that same flywheel from further behind. And yet, methanol still contains carbon. Green methanol, the kind made from renewable hydrogen and captured carbon dioxide, is expensive and scarce. The same problem as green ammonia, except ammonia at least has no carbon to begin with. If the IMO's 2050 net zero target is taken seriously, methanol may be a bridge. Ammonia might be the destination. The IMO approved interim guidelines for ammonia as a marine fuel in 2025. Regulatory frameworks are being written, and the first commercial engine deliveries are scheduled for 2026. A Norwegian platform supply vessel is slated to run on ammonia that same year. The honest answer to whether ammonia wins is that nobody knows. The shipping industry is placing bets on multiple fuels simultaneously because no single answer has emerged. LNG for the near term, methanol for early movers, and ammonia for those who believe the 2050 target is real and that the cheapest zero carbon molecule eventually wins. Everllence built an engine. That part is done. What happens next depends on ports, regulators, green fuel production, and whether the dozen or so companies currently willing to be the first movers pull enough others along with them. It usually doesn't take much, just enough people to make it feel less like a gamble.